Optimization systems manage logistics for hospitals, supply chains, and power grids, yet they operate almost entirely as slow, asynchronous batch jobs in the background. Standard constraint-solving toolsets evaluate these logistics by loading massive clause sets entirely into active RAM. This memory requirement severely bottlenecks processing speed. For the user, the result is a rigid workflow. A human planner clicks an Optimize button and is forced to wait 30 seconds, or sometimes overnight, for the system to return a single valid schedule. By trapping complex optimization within a batch job architecture, the system isolates constraint resolution from active human workflows, limiting the capabilities of enterprise software. Changing that dynamic requires pulling constraint resolution out of the batch queue and putting it directly onto the real-time user interface request path. We see the difference directly here. On the left, a traditional loading spinner. On the right, dragging a workload instantly highlights and repairs 50 constraint violations. The mathematical reality requires dropping latency to single-digit milliseconds. Reify, along with its streaming backend Navokoj, is a deep tech stack engineered specifically to solve this exact latency problem. To reach these speeds, traditional direct solver APIs have to be abandoned. Interactive optimization requires compiling decision models into specialized formats rather than invoking them through a standard API. Writing pure conjunctive normal form, or CNF, for real-world scheduling logic is archaic and difficult for product engineers to maintain. To bypass this, Reify operates as an embedded domain-specific language, built natively within the deprogramming language. This code snippet shows a declarative policy. Instead of manual Boolean clauses, developers write high-level variables and exact cardinality groupings to define their constraints. Reify leverages D's compile-time function execution, or CTFE. CTFE evaluates types and dimension filters at compile time, executing the structural logic well before the application actually runs. This allows the compiler to collapse the Cartesian product early. Impossible variable combinations are identified and discarded before they can ever be generated. Defining decision semantics at compile time radically shrinks the problem space before the solver even touches the raw data. The first active compilation step translates that declarative model into an abstract syntax tree composed entirely of expression nodes. At this stage, the primary threat to maintaining a sub-4 millisecond latency target is garbage collection. A single GC pause stalling the thread ruins the execution speed. Reify pre-allocates contiguous node chunks, bypassing garbage collection entirely. Why use D instead of Rust? Resolving constraint networks requires constant graph mutation. Rust's borrow checker introduces severe friction here. D provides raw pointers, allowing natural mutation without a GC pause. D was chosen strictly for its architectural fit, offering the zero GC systems capabilities needed to build a constraint graph without a boilerplate tax. Once the abstract syntax tree is built, it must be converted into a portable execution artifact. This visualization tracks the linear Titan transformation process. Non-clause logical rules pass through this filter and are translated down into raw, normalized CNF clauses, packaged as a JSON solver artifact. This artifact decouples high-level domain semantics from backend execution geometry. A dedicated routing engine intercepts the artifact, reads its structural signature, and determines the optimal execution backend for the specific problem shape. Categorical and all diff models require direct n-ary state satisfaction, so the router sends them directly to accelerated GPU Q-state engines. Workloads heavy in soft preferences are routed to continuous Riemannian max-sat solvers. Standard symbolic logic workflows are routed down the default path to the low-latency Nitro CPU engine. By automating the routing process, product engineers write a model once and trust the compiler to match it with the correct hardware and mathematical engine. The final execution phase begins when the routed artifact reaches the Navokoj backend. Traditional conflict-driven clause learning solvers possess a critical flaw at enterprise scale. They must hold the entire massive clause set in active RAM simultaneously. A traditional solver's RAM usage expands under millions of clauses until it crashes. Navokoj v3 bypasses this with a streaming architecture. By converting clauses into a binary stream, the memory state remains bounded, solving 116 million clauses on just 10.7 megabytes of RAM. When operating on standard symbolic benchmarks, the Sutra microkernel achieves a median latency of exactly 3.7 milliseconds. On the canonical server scheduling benchmark, the engine processes 403 hard clauses in 223 milliseconds to reach a 99.95% satisfaction rate. Streaming architecture removes the memory wall, providing millisecond completion times on models with millions of clauses. Following the solver's output back up the compiler pipeline, Reify hydrates raw Boolean assignments back into human-readable domain objects. Reify enforces a principle of zero-trust execution. The backend solver's mathematical output is never blindly accepted as the source of truth. Raw output maps back onto the domain AST nodes. A local verification step rechecks every assignment against the D model in microseconds. Concurrently, the explainability engine generates physical telemetry, detailing VRAM usage, credit estimates, and causality blame scores for any conflicts. Strict local verification and transparent physical plans protect complex enterprise applications from silent solver hallucinations. The entire pipeline is a continuous mechanism. Declare the decision space, compile it into an artifact, route it to the optimal geometry, execute via stream, and locally verify the results. This degree of architectural engineering exists for one distinct purpose: to alter the user experience. It fundamentally shifts the software environment from sluggish, asynchronous overnight batch optimization to a hyper-reactive, fully interactive workspace. Operating in single-digit milliseconds turns optimization into a baseline UI feature, making constraint solving function like a spell checker or a collaborative text editor. The Reify compiler and Navokoj backends integrate complex optimization directly into the primary application loop.